Good day, future engineers. Perhaps you are getting busier this time with all your subjects, but I hope you are still doing well with your studies. For today, let's talk about the kinematics of particles, specifically rectilinear and relative motion. First, let's look at our objectives for this lecture. With today's discussion, we aim that you will be able to describe the basic kinematic relationships and apply those kinematic relationships, and we will be able to use properly the sign and direction of acceleration and velocity. And then we will go with the analysis of rectilinear motion as well as relative motion. Previously, we defined important terms for this subject. You learned that kinematics of particles is the study of geometry of translational motion without reference to the cause of motion. Take note that this time, in this definition, we specified a type of motion, which is translation, because particles can only move by translation and not by rotation. Also, kinematics does not depend on applied forces and the mass of the particle or object. In the previous lesson, we defined and saw examples about rectilinear motion, that it is simply motion along a straight path. Previous examples are traveling car with constant velocity and freely falling bodies for constant acceleration. When we say uniform rectilinear motion, it means motion with constant velocity. And when we say uniformly accelerated, it means motion with constant acceleration. Rectilinear motion can be described by the following. First is time. Time is typically expressed as seconds for both SI and US customary units. Next is position, which is used to locate a particle from a reference point. Always remember that position is a vector quantity. Therefore, it is defined by both magnitude and direction. To visualize, let's consider the straight path expressed in meters, and then let's denote a point at 0 meter as our reference. Anyway, setting reference is based on your preference. So let's say for a given particle at A, we can denote its position from the reference as x sub A is equal to negative 3 meters. And then for a given particle at B, we can denote its position as x sub B is equal to positive 5 meters. Similarly, we can say that particle C is positioned at negative 7 meters from the reference. So that's position. Now let's proceed with displacement. Displacement, another vector quantity, is used to describe the change in position of the particle. It is actually the difference between final and initial position. Referring to the same figure, let's assume that a particle travels from point A, then to point B, and then to point C. To compute the displacement of the particle for the entire travel, as described by this dark red arrow, we should write delta x is equal to x sub f minus x sub I, in where delta x means a change in position, or in other words, the displacement. X sub f is the final position of the particle, and x sub I is the initial position. To address this specific situation, we should rewrite it as follows. Delta x sub point A to point B then to point C is equal to x sub C, the final position, minus x sub A, the initial position. Notice that displacement only depends initial with the initial and final position. So now substituting the values, displacement is equal to -7 minus -3 meters. Don't forget to carry the signs of the position, since we are dealing here with vector quantities. Finally, we can conclude that the displacement of the particle as it travels from point A to point B and then to point C is equal to -4 meters, or 4 meters to the left. So that's displacement. Now, let's proceed with distance, which is a scalar quantity used to describe the total length traveled by the particle, either through straight or curved path. By referring to the same figure and assumed situation, we can compute the total distance traveled by the particle by writing distance point A to point B and then to point C is equal to distance from point A to point O, which is the reference point. Let's say at 0 meter, that's point O, plus distance from point O to point B, plus distance from point B to point C. Observe that d sub BC can be broken down into d sub BO plus d sub OC. Substituting the values, total distance is equal to 3 meters plus 5 meters plus 5 meters plus 7 meters. Take note that we only use the absolute values. Remember that distance is a scalar quantity. Its value does not depend on the direction, and there is no such thing as negative distance. Thus, the total distance covered by the particle from point A to point B and then to point C is equal to 20 meters. You may notice from now on that the total travel distance is not always equal to the magnitude of displacement. Next, we have velocity, a vector quantity which is simply displacement over time. Also, we have speed, a scalar quantity and is simply distance over time. Lastly, we have acceleration, a vector quantity which is the rate of change of velocity with respect to time. The formulas and concepts behind speed, velocity, and acceleration will be discussed on the next part of this lecture. So that's it for now, class. Thank you and God bless.